Hey there, everybody. Today I want to take you through the ins and outs and show you the nuts and bolts of PCA, LDA, and SVM. This is very interesting. I think you're going to learn a lot and very useful too. This lesson is very practical. I try to make all my teaching lessons practical and show you real world applications for all kinds of machine learning algorithms, data science tools and techniques and methodologies and financial investment strategies. Try to show you how the rubber meets the road and how you can use this stuff to do things that are actually useful and practical rather than just something that is more abstract or obscure and potentially useless. These three tools are very useful. Okay, so PCA stands for Principal Component Analysis. It's basically a dimensionality reduction technique used to take a high dimensional data set, which could be a dozen columns of data up to hundreds or even thousands of columns of data, and focus on just the top most relevant types of features that are going to have the biggest impact on the target variable that you select, right? When you're trying to make predictions in the machine learning world, you have independent variables, which will have an influence on the dependent variable, right? The dependent variable is dependent on the independent variables. We'll see an example of that in just a minute. So another technique is linear discriminant analysis, LDA. This is a supervised dimensionality reduction technique that focuses on finding linear combinations of features that best separate two or more classes. So like the PCA, which is unsupervised, this is actually supervised. We'll see how that works in just a minute. But again, it's dimensionality reduction technique where you take lots and lots and lots of features in your data frame, basically lots of columns. You can call them columns or features. Most people call them features. And you reduce them down to the most important features. Okay, if you have 100 columns in a data set, or God forbid, thousands of columns, I can guarantee that most of those will have no impact whatsoever on the target variable, but some of them will have a high impact on the target variable, right? So these techniques will help you figure out which features have the most influence on that target, okay? The last thing we'll look at is SVM. This stands for Support Vector Machine. Again, this is a supervised machine learning technique used for classification, sometimes regression. It's more classification though, and helps to find hyperplanes that best separate points or differences in the classes with the maximum margin. Okay, so again, we're taking lots and lots of features and reducing or distilling it down into just a few features that are the most salient or most relevant or most important. Okay, so sorry for that. I'm getting a call from a recruiter, most likely because I don't identify the number. And I get 50 calls from recruiters every single day. Most of them are complete nonsense. So let's not go off on a tangent there, but rather refocus our attention on this Titanic data set. So we're going to pull this from a source online. This comes from Stat Model, abbreviated SM, and Seaborn has this data. I guess they collaborate or cooperate together to put this together for us. So there's several different sources for Titanic data. You can download the CSV. I like this one because it's dynamic. You can read straight from the API endpoint. Well, lots of distractions today. Now my light goes off too. So I have a motion sensor in the room here, and if nothing moves around, the sensor figures that you're gone and it shuts the lights off. Okay, so no more phone calls, no more motion sensor stuff. So we have the data pulled in. This is our Titanic data set. So we have who survived, the passenger class 1, 2, and 3, sex, age, parch. Not even sure what that means. Fare. This is how much they paid to get on the boat. $71. That is first class, and this is third class, $7. Right. So this makes sense. So lower class is third class. This guy paid $7. This guy paid $71. This is a class third. This is first. Okay, we see that it's female, gender, embark town, alive or alone. Okay, were they traveling alone or were they with a group? So we have the one-hot encoder, and we are going to label and code this data. So this is interesting because we have numeric data. The machine learning algorithm will parse through this quickly and easily. All these things are fine. This, the machine learning algorithm doesn't know what that is. It doesn't know male, female. It doesn't know third is third class, first is first class. Doesn't know man, woman. Doesn't know true or false. It doesn't know the town where the passenger embarked from, right? That's where they got on the boat. It doesn't know any of these things, but it knows numbers. So we're going to take everything that's a number and encode it, everything that's, sorry, not number, and encode it into a numerical representation of male and female. Okay. survived. Do we have that? Let me look at it here. Two survived. Oh, where was that? Let's see that. Passenger class. Oh yeah, so these numbers, so this stays the same. Um, the age of the passenger. Okay, so everything is going to be converted into a label. So I have a video about how to convert numerical data into I'm sorry, to convert label data into numerical data. There's basically 3 days. You can do one-hot encoding, you can do categorical encoding, or label encoding. So I have a video that explains the differences between the three. My personal preference is label encoding because you don't increase the number of columns. If you start with 12, you have 12 at the end. If you do one-hot encoding, you can have hundreds or even thousands of columns if you have high cardinality data sets. Cardinality is the number of unique items within one feature of a data set, right? So I'll take zeros and ones and plug in a 1 for every true that it sees, and 0 would be false or it'd be nothing. One encoding or the categorical encoding. I like label encoding. It's just clean, crisp, very straight, easy to set up, execute, and easy to understand and interpret too. So I'm a big fan of that. Check out the video if you want to learn more about that. So we have separated the numeric and categorical columns, okay, and we're going to treat them as essentially numeric or some type of a label encoding metric, okay? So let me go ahead and run this, and this is the first analysis here. Let me look at something quickly. PCA. Oh, that's fine. That's fine. Okay. So hit run. Go ahead and run it. And we are going to take everything from this data frame. Drop these. Survived is the same as, what was this? I was looking at this earlier. Alive and survived are the same, right? So this would be duplicating the data. We just need one. We're going to drop something we don't need. PCA and PCA2 and ignore, and we are going to look just at survived. So if we take this out of the data frame and treat this as a independent variable, x is independent, y is dependent, so it's dependent on x is independent, it can be whatever it wants. You have to drop this if you're going to use this as a dependent variable. If you use this over here, you're going to have a big problem. I think it throws an error or you have some really wonky results. So you have to drop anything from the original data frame that you're using as a target variable, okay? So that's how that works. And you can tell that this is unsupervised, right? So PCA is unsupervised because the first part of the algorithm right here, we're taking all the categorical columns, getting dummies into our data frame. If I print this data frame, let me try to do this real quick. Display df. Okay, and then it's just gonna get everything underneath. That is fine. Control Enter. And it's saying categorical fill with nans. Oh, I think I have a nan here. Let me take a look at something here. Let me see if I can resolve this thing. I wasn't expecting nans because I did look at this earlier today, and I know it worked because I had the code, I had everything set up. I must have changed something just before I turned on the recorder here. So let's see if we can quickly get this thing buttoned up. Let me take a look at this thing here. Don't want to go too far off track, but when this happens, you have to dig in, you have to do a Google search and look at the error message and then just figure it out, right? You have to figure these things out because if you don't do it, nobody's going to do it for you. Single position index is out of bounds. That sounds weird. Display, that should be fine. And the error occurred. Categorical columns. Let me look for this thing. Where's it actually occurring? It sounds like there's a nan in the data, but there shouldn't be. Did I not run it? Let me just try this again. Maybe I just didn't refresh or something. Let me try this again. Okay, there's the head of the data frame. Okay, so that was a glitch, I think. There's no real issue here. I might have had another data frame that I loaded and it was looking for a different variable that contained different features or something like that. That can happen too. Okay, so I think we're fine. We're looking at the data frame. Oh, no, it didn't. PX scanner. Oh, PX is not defined. Oh, I know why. PX is not defined. So Oh wait, let me do a quick Google search here. Import Plotly as PX, I think. PX, I think that's it. Is that literally it? I do a lot of hacking here, so I switch back and forth between different environments, and sometimes these things get a little bit jammed up because it's looking for data from one side that actually wasn't even pushed into this other Plotly Express. Oh yeah, Plotly Express, not just Plotly. Okay, so let's go back and we can put that right here. Yeah, that's fine. Okay, that's fine. Okay, so we set that. We'll set that just to refresh everything. This should be good to go. Okay, show the data frame. And our chart is going to work. Yes, we got it. Okay, congrats. Pat yourself in the back. Double thumbs up. Oh, we got it. Okay, so here's the PCAs. We have the visual of the data frame. I just want to take a quick look at that to see what that looks like. And here's the PCA principal component analysis plotted over here. So if you look closely, we have PCA component number 1 and component number 2. And I printed this out, I think. Yeah, okay, so here's the explained variable. So the first most influential independent variable that influences the target variable, the dependent, is 21% influence and a 15% influence. Okay, so I think I have that in my notes over here. 21%, yep. So the explained variance of the first most influential variable ratio is 21%, and the second highest is 15%. This is a measure of how much each component contributes to the overall variance of the data. Remember, we want to look for the number 1, number 2 highest variances in the data set. Most of them are going to have no variance or very small, 1, 2%, or just a small piece of minutia of 1%, right? But these are the two biggest. So these will have the two largest impacts on the data set. So PCA1 is plotted here, it's in yellow, and PCA2 is in dark blue or purple or whatever this thing is, right? We can zoom in a little bit on this and get some finer details here, and then double click to zoom out. So everything is plotted here. So we see that the PCAs, that looks nice. We have our plot, we have our data set up above. Let us look at okay, still PCA. We're going to look at a standard scaler. We're going to scale everything. So if you scale it, take everything and you kind of normalize it to the same basic reference point. So if you have outliers or big numbers on one side and small numbers on the other, this will take everything and reduce it to a more normalized, more well-structured data set. So you don't have big outliers pulling your data in one direction or the other, or a lot of small outliers pulling your data in the opposite direction. We want this kind of structured, normalized, more of a normal bell-shaped curve, more normal distribution. That is the goal here. Okay, we don't want big influences coming out from these outliers. We see PCA1 and PCA2 as bars here showing you the percentage of influence, and then the cumulative percentage is rising up over time. You can see this gets to 1% by the time it gets to the northeast part of the chart, and each one is taking a step up, showing you the relative contribution of each PCA component to the overall influence on the target variable. So if I go up, it looks like PCA1 is about 0.29 and PCA2 is about 0.21 or 22. And that's what we see over here, 0.21 and 0.15. Wait, is that what I had? 0.15 and just over 2.0. Okay, so those are the explained variance ratios right there. And then this is everything plotted right here with the different components 1 through 9. Okay, so we have that, and then you can see the measurements over here, 0.33, 0.23, so that's the amount right there, 0.33, almost 0.4, not quite, 0.23 goes over that, and 0.15, close to 0.15 right here, and that's what you see for component number 3. Okay, so I think we're looking good. Do we even need this? I think I changed something around, reduced to 2 components. We already had to, I think. Okay, so the next cell here, let's run this. And I think we can wrap up the PCA part of this. Let's do the same thing. Okay, so I had some duplicate thing over here. Let me get rid of this and get rid of that. That is superfluous. It's extra. It's unnecessarily there, and we don't need it. Okay, so let us look next at standard scalars. PCA, yeah, okay. So we have one more plot over here For the principal component analysis, right, we have the standard scalars over here. We're taking the scalar, anything that's numeric is coming from this part of the data frame over here. If you look over here, here's the data frame and all the numbers. So we're looking at survived, class, age, B slip, Perch, fair. These are all numerics. Anything that's not numeric, we're just going to skip it. Okay, it can't be fed into the algorithm for analysis because computers don't understand words. They understand numbers. Excellent, but no words. So we plot the chart. You'll see that the PCA components for 1 and 2 represent the directions of the maximum variance on the data, right? So we want to see which features have the maximum differences, right? That's what we see over here. Feature number 1, PCA1 and PCA2. It accounts for basically about 50, almost 57% of the overall variability of the data is composed of just 2 features. If you look at the bottom 2, you have just about 3% of the variability of the data explainable by the bottom 2 features. Here you have about 55% or 56%. So the first 2 features really have the most impact on the outcome. Here's the scatter plot again. Light color is no, and dark color is no. Okay, so survived 0 equals no, did not survive. They passed away on the fateful voyage, the first time the Titanic crossed the Atlantic. And if they survived, you get a yellow dot over here. And if we zoom in, we can actually see the PCA angles and the direction. The direction and the length of the line shows you the influence. So PCA and PCA 1 and 2 have the most influence. Survive fair, age, Parch, ice slip, and what is this? Passy? I don't know what that is. Sorry. You have the gender of the passenger, PCA 1 and 2. These are the biggest, right? They have the most influence. And that's exactly what you would see over here. PCA 1 and 2, again, account for about 56% of the variability of the data, right? So the arrows of the features show you the similar directions that contribute to the overall similarity or the differences of the components, whereas the features plotting in opposite directions have contrasting effects, right? Again, if you zoom in on this, on these arrows here, this is kind of muted. This is kind of subtle over here. You can see PCA arrow goes up a little bit towards 1 o'clock on the chart. PCA 1 goes to 3 o'clock, and then these others go in different directions, either clockwise or counterclockwise. Take your pick, it doesn't matter. It shows you the direction of the arrow, and the length of the arrow shows you the overall influence. So that's PCA. Let's look at LDA, linear discriminant analysis. So this is more of a supervised methodology. The first one is unsupervised, right? Unsupervised is more clustering. You dump everything into the model and say, tell me what's going on. You tell me what is the PCA, what are the LDA, sorry, not LDA, we're doing that next. What's the PCA and what are the top influences of the components for that principal component analysis, right? So I don't know what to expect. I'm just telling you, these are the components. You tell me what that means. That's unsupervised. It's like clustering. Supervised is when you know what you expect and you want to see how accurate the model is in making predictions, right? And SVM is supervised too. So PCA is unsupervised, LDA is supervised, and SVM is supervised. Let's scroll down to the LDA piece here. So we're going to run this. Okay, you can see the model is performing pretty decent. Precision 0.86, 86, 86, 0.7. We want this to be at least 0.70 or higher. This is okay, 0.86. 0.9 would be better, closer to 1.0, like 0.99, 0.98 is better. 0.77 is bearable. We can live with that. It's just how accurately the model is basically able to learn and to make predictions. This is the precision, the recall, and the F1 score. So again, closer to high 0.9, 0.95 to 0.98 or 99 is ideal. You will almost never get 100% unless the model is overfit or unless the data set is very tiny and the computer really hasn't been able to learn very well and make predictions very well. You can see 1.0, but realistically it's like about 0.9 to 0.9596. That's what you typically see, right? So LDA, continuing on, we can plot the results here. We see the LDA component versus the target variable. Control Enter to run it, and we get the chart. Now this is very different from PCA. You don't see all the fancy angles of the components moving in different directions, pointing to different numbers on the clock, right? These just have basically single axes that cause them to look like just straight lines, okay, separated by their labels. the plot has one component. It doesn't show data spread like the other 2D chart we saw with the PCA. And this is more informative visualization. The PCA shows you more insight, more information, right? The PCA shows you the different components. Just this one just shows you on a single axis where the points are aligning, okay? So LDA, again, is supervised. It's a little bit boring. PCA is a little bit more interesting, and that is unsupervised, right? So you don't know what the outcome is. The LDA, you know what the outcome is going to be, right? And you test for that. So let me go ahead and run this, Control Enter to run it. And we have the LDA components, okay? This is number one because we take the first one, and here we take the second plus one, okay? In Python 0 base, so 0 is kind of 1 in the real world, and 1 or 0 plus 1 is 1. This would actually be 2, so this is 1, this is 2. And we're going to plot it again. We have the decision boundary. Everything lines up on the decision boundary. LDA is really used for classification types of problems. So numeric type of problem would be more regression. That would be like the age of the person who passed away on the Titanic. If you fed in all of the details over here. If we go back here, if I fit in all the details except for the age, survived class, P class, sex, let's skip that. We'll predict that, and we will feed these into the model. I can predict the average age of the person passing away, right? That's a regression type of problem. A classification problem is very different. It's like true or false, yes or no. It's a label, man or woman. That could be a classifier. What class they're in, first, second, third. Adult male, adult female, embark town. You can predict all of these, right? If you have all the other variables, that would be a classification type of problem. It's more labeled. It's non-numeric, right? Man, woman, classification, gender, embarking town. Anything that's numeric, passenger class, age, what else? SIB slip, whatever that is. Honestly, I don't even know what that thing is. Those would be numeric, so you could predict those using the regression regression technique. And if it's not regression, it's classification. So you're looking for labeled data, right? So that's the difference. So here, let's create a quick heat map. Name LDA class is not defined. Why is that not defined? Again, I think we have a glitch here. Let me refresh that. And LDA class separator, it should come from the prior LDA class separator. Is that, hey, did I change this thing again? Sorry about this, guys. LDA class separator. Oh, it must come from up here. I must have accidentally deleted something because it has to be created dynamically. Oh, I apologize. I'm sorry, guys. I'm sorry. I did this once before too. Let me swing back when the video's done. I don't edit these, and I don't stop the video. I just run it straight through. One of these days I have to learn how to edit, and then I could just handle the problem. I could turn off the recorder, handle the problem, and then turn on the recorder and finish the video, but I don't know how to do that. I do these all by myself. I don't have a team that helps me, right? So a little bit frustrating. I must have had this because this did work before. Now it's not working. I swear I'll swing back, fix this after I'm done recording. Let's just get to the end of this. So you have a mostly coherent video. I apologize for this. I'll fix this before I post the source code, which I'll do later today. Just give me a little time to get back to this. So just imagine that this is working. Here we have the SVM, so support vector machine. Again, this is a, what is it called? Supervised technique where you know what the outcome is, right? You're trying to classify a certain outcome, and you know here, now this data set is kind of small, so we're getting close to 100% precision, actually perfect precision recall and F1 scores, and the same with the accuracy. It's accuracy 1.0 across the board, and SVM accuracy total is fine. Let me go ahead and refresh this. That is up to date. Control Enter, and here we have a plot with our PCA defined data frame, and why numeric is not defined. Why is that not defined? I'm sorry, guys, because this was all working before I turned on the video. Is this the first? Oh, why numeric? Yeah, that has to come dynamically from the label. I don't know why. Sorry. This could have been done a little bit better. Apologize for this. I will fix this before I post the video. I will fix up the code, and you'll have fully working code when you download this code later today. Let me swing back and get the stuff. My intent was to do this linearly straight through without any kind of issue or we fall into a pit here and got stuck. But I'll tell you what, I'll fix this up before I post a video later today. Let's wrap up the video and then I'll turn off the recorder, fix the problem, and then post that maybe 15 or 20 minutes, give me a little time to get back to this, okay? So PCA is principal component analysis. Again, unsupervised learning method. LDA is linear discriminant analysis. This is a supervised technique like SVM. We're looking for the support vectors. Again, these vectors show you the parallel or the orthogonal vectors that support the overall balance or remainder of the data frame, but these support vectors have the primary influence, right? Like LDA and the PCA. We're looking at the primary components that support the overall analysis, okay? So that's it. I have a couple more notes over here. You can read through that at your leisure. I'm not going to take you through it. It's spelled out pretty nicely over here. So I think you'll have all the details that you need and probably some excess details too. I'd rather give you a little bit more than a little bit less. Then you don't have any questions at the end of this thing, and everything is fulfilled to completion. I just have to go back here and fix this guy and fix this guy. So I'll take a look at that. Give me 15, 20 minutes. It'll be in a good state. Okay. So that's it. PCA, LDA, SVM. We have some nice charts. We decomposed the data sets into its various linear discriminant pieces, and we created some nice charts and created great insight around this data set. Okay, so that's it, guys. Just wanted to introduce you to these very common topics that you will see inevitably on your journey in the data science realm. Okay, so I'm gonna wrap up the video. I'll fix these issues and I'll post the updated fully working code in just a little bit. Thanks for your time today. Enjoy the rest of your day. Goodbye.